All right, now recording. So today I'm going to do a lot more curve sketches. That was the main idea. Section 4.5. Okay, so I did a couple already, but I'll do maybe 4 more out of this list. So schedule-wise, we're here. Okay, we're not scheduled to do 4.6 at all, so never mind about doing 4.6. All right, so back to curve sketches. Again, there's a super long list of stuff you want to analyze from 4.5. And we'll consider all of these. Page 315. So domain, intercepts, symmetry, asymptotes. Page 316. So that was all pre-calc stuff. Then calc stuff, intervals of increase and decrease, local max and min, concavity, sketch the curve. Okay. Again, on the exam, if I make you do the entire problem, it would have to be something quick, something that you can do fairly easily. Otherwise, I'll just have you do a portion of it because I realize it sometimes takes a long time to do these problems and you only have an hour to do the exam. Okay. So here we go. First about the in-class assignment yesterday. Limit x approaches 0 of 1 minus cosine x over x. That is 0 over 0. If I plug in 0, the cosine of 0 is 1. So you have 0 over 0. L'Hopital's rule does apply. Derivative of 1 minus cosine x is sine x divided by 1, which means you plug in 0 and you get 0. Okay, so there we go. All right, so I was going to show you problem number 9. And then 13. And then let's see what else was I scheduled to do. Maybe 29 and 45. Complete analysis of that. Okay. So question number 9. Y equals x over x minus 1. All right. So the domain is all real numbers except for 1. You're not allowed to divide by 0. So all real numbers minus a set consisting of 1. Intercepts, when I plug in 0, you get 0. And if y equals 0, the only way that's true is when the top is 0, 0. So the only intercept is 0, 0. Okay, symmetry. To check for symmetry, you plug in negative x. Okay, so put negative x here, negative x here. So I get negative x over negative x minus 1. Is it the same as the original? No. Is it the opposite of the original? No. So I have no symmetry. And you kind of know there isn't any symmetry just by the domain, right? I mean, -1 is allowed, but 1 is not allowed. So that kind of already indicates to you that there's probably not going to be any symmetry. Okay, let me try to get the curl out of this paper here quickly. Okay, asymptotes. You know, vertical asymptote is x equals 1 automatically. Horizontal asymptote. See what happens when x approaches infinity. And also negative infinity. So limit as x approaches either plus or minus infinity of x over x minus 1. That's very easy. Okay, I can use L'Hopital's rule. That's going to be infinity over infinity. So the derivative of the top is 1, derivative of the bottom is 1, so you get 1. So y equals 1 is a horizontal asymptote. Okay. A side note, before we did L'Hopital's rule, we actually could do this a while back. The trick was to divide top and bottom by x. Remember doing something like that? You divide top and bottom by x, you get 1 over 1 minus 1 over x, and 1 over x approaches 0. Okay, so that was another way to do that. Okay, so there's domain, intercepts, symmetry, asymptotes. And by the way, yes, I realized probably for this whole semester, I'm going faster than I normally might face-to-face, and it's because I know that we're recording. So you can always go back and play the video. I mean, that might still be a good idea when we finally get back to face-to-face to have the lectures recorded. But since I know you can always go back and play the video, I may be going faster than I normally would if we had met face-to-face. Okay, but in any event. All right, so the calculus stuff. Do your first and second derivatives. So that looks like a quotient rule. So y prime bottom, x minus 1, times the derivative of the top, which is 1, so I don't have to put anything, minus the top, x, times the derivative of the bottom, which is also 1, all over x minus 1 squared. X minus 1 minus x cancels out, negative 1 over x minus 1 squared. And I can automatically say that's less than 0 for all x not equal to 1. Okay. X equals 1 is already not allowed. Okay. If I plug in any number besides 1, this denominator is going to be positive, right? There's a square. And I'm sure I can cover it up and show it to you at the same time. So the bottom is positive. The top is negative 1. So negative 1 divided by positive automatically is less than 0. So that means this graph is decreasing everywhere that it's defined, which is all real numbers except for 1. So the function is decreasing from negative infinity to 1, union 1 to infinity. It's always going to be going down. F is increasing nowhere, so there's no max or min. Okay, second derivative. For taking the second derivative, again, think of this as negative 1 times x minus 1 to the negative 2 power. Right? Again, I would not use the quotient rule here because the numerator is a constant. Treat this as x minus 1 to the negative 2. So negative 2 is the exponent. So y prime looks like that. So y double prime, negative 2 times negative 1 is 2. X minus 1 to the negative third, there should be a negative there. To the negative third, which is 2 over x minus 1 cubed. All right, normally I would set it equal to 0, but this expression can never equal 0. The top's already 2. Right? I do want to lay down on my number line 1. The concavity might change at 1 just because that's an undefined point. Okay, pick something less than 1 like 0. 0 minus 1 is negative. Negative cubed is negative. 2 divided by negative is negative. Look at a number over here like 2. 2 minus 1 is 1, positive. 2 divided by that is positive. Concave down, concave up. Right, so the function is concave down from negative infinity to 1. Concave up from 1 to infinity. I do not have an inflection point, even though there's a change in concavity. The best way to say I don't have an inflection point is because I don't have a point. There is no point 1 comma anything. So there is no inflection point. Okay, you would have to say 1 comma something. An inflection point implies a point, but there is no point. Okay, no ordered pair that's there. All right, so here's the graph. Asymptote y equals 1, x equals 1. Only intercept is the origin. Always decreasing. Let's see. Always decreasing. So here we are, decreasing, decreasing. This side, it's concave down, upside down U shape. Asymptote y equals 1, asymptote x equals 1. Here, still decreasing, but concave up. Asymptote, asymptote. So that's the entire graph. Okay, and let me raise this up again so for focusing purposes, and with the paper. All right, so functions that have asymptotes are always a little harder, as you might guess. All right, so that's it for that one. Okay, next one I want to show you is 13. Okay, y equals x over x squared minus 4, which factors into x over x plus 2x minus 2. All right, domain, all real numbers minus the set consisting of negative 2 and positive 2, right? Can't plug in negative 2, can't plug in positive 2. Intercept, origin, plug in 0, you get 0. If y equals 0, again, that means the top is 0. How do you make the top 0? 0. Symmetry. f of negative x, put negative x right there, negative x right there, but negative x squared is the same as x squared. So I have negative x squared minus 4. That is the opposite of the original function. It's negative f of x. So by definition, f is odd. You will have origin symmetry, symmetry with respect to the origin. All right, asymptotes. Okay, we already know we have x is plus or minus 2, vertical asymptotes. X is negative 2, x is positive 2. Horizontal asymptote. Limit as x approaches either plus or minus infinity of x over x squared minus 4. That's infinity over infinity. I can do L'Hopital's rule. This gets big, this gets big. So derivative of the top is 1, derivative of the bottom is 2x. Limit as x approaches either a positive or negative infinity. It doesn't matter if I plug in a super big positive or super big negative, the ratio approaches 0. So horizontal asymptote is y equals 0. And we've actually seen this theme before, right? From the original, the top is first degree, the bottom is second degree. The second degree is going to win in the long run. Okay, if I plug in a billion is big, but a billion is nothing compared to a billion squared. Minus 4 is insignificant, so it's a very small number. All right, so I have asymptotes at plus or minus 2, x equals plus or minus 2, and where did it go? Y equals 0, same as the x-axis. Okay, now for the calculus part. It's not so nice. So x over x squared minus 4, quotient root. Okay, the denominator is going to be x squared minus 4 squared, right? Let's get that out of the way. X squared minus 4 squared. Numerator, bottom times the derivative of the top. The derivative of the top is 1. So x squared minus 4. Minus the top, x, times the derivative of the bottom. Derivative of the bottom is 2x. Over, as we said, x squared minus 4 squared. Okay, distribute this out. X squared minus 4 minus 2x squared, or negative x squared minus 4 over x squared minus 4 squared. Okay. And once again, this is less than 0 for all x not equal to plus or minus 2. Okay, so I don't have to set it equal to 0. Okay, if I look at this thing, the bottom is automatically positive, unless I plug in plus or minus 2, which I'm not doing. And I claim the top is always negative, right? Look at x squared, non-negative. Put a negative in front, now it's non-positive. Non-positive means 0 or negative. And then I subtract 4, it's got to be negative. So it's a negative divided by a positive, so less than 0. So here's a case again where the function is always decreasing wherever it's defined. Okay, so I write it as f is decreasing from negative infinity to negative 2, union negative 2 to 2, union 2 to infinity. F is increasing nowhere. So once again, we have no max or min. Okay, double prime is really not very nice at all, but the results actually pretty good. Okay, so here is my first derivative. So for y double prime, quotient root. Okay, first, let's get the denominator out of the way. What's the denominator squared? It's x squared minus 4 squared, squared. Fourth power, right? Again, by formula, I'm supposed to square the denominator for the quotient root. So x squared minus 4 squared, squared is the fourth power. Now quotient root. Bottom, x squared minus 4 squared times the derivative of the top. Derivative of the top is negative 2x. Minus, it's a double negative, so right now pretend it's minus. The top, negative x squared minus 4 times the derivative of the bottom. Derivative of the bottom is a chain root. 2 times x squared minus 4 to the first power times 2x. Okay, so now that was a negative, that's a negative, that's a negative. So that's why I make this plus, plus, plus in red. Okay, so the original was in black ink. negative, negative, negative. Distribute the negative here, make them all pluses. All right, then what I decided after that is to factor out the greatest common factor. They both have a 2x, right? There's a 2x there, 2x there. They both have an x squared minus 4. There's an x squared minus 4 squared, x squared minus 4. So I factor out an x squared minus 4 to the first power, because I'm going to combine it with that later. All right, so what's left over here? I took out a 2x. I still have a negative 1. I took out an x squared minus 4, but since it's squared, I have one more, x squared minus 4. Plus, again, these are all pluses now. I took a 2x out. I still have that 2. I took that out, and I still have an x squared plus 4. Okay, so again, that came out, so I still have a 2 x squared plus 4. Now, x squared minus 4 to the first power, x squared minus 4 to the fourth power. I can cancel one of these with one of these. So my new denominator is going to be x squared minus 4 cubed. Okay, here's a 2x. Combine like terms here. That's negative x squared plus 2x squared, which is x squared. And then I have positive 4, right? Negative 1 times negative 4, plus 8, which is 12. And then, yes, I would set that equal to 0. This does have a solution. When is a fraction 0? Top is 0. This can never be 0, right? X squared plus 12 is always positive. So the only way to make it 0 is for x to be 0. So I have the origin as a possible inflection point. Okay, I have to turn the paper over. I don't want to show you this yet, so yeah, I'll just show you this for focusing purposes. On that. And that. All right, so let me do my sine chart for the second derivative. All right, I lay down the critical number for the second derivative and wherever the function was undefined. Undefined at -2 and 2 and also 0. So I have 1, 2, 3, 4 regions to check. So I picked something over here like -3, something here like -1, something here is +1, something here is +3. I will plug in, I check the sign. What do I know about x squared plus 12? Always positive. So plus, 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 plus right away. Okay, so I just have to check that and that. Okay, 2 times -3, negative. So you can be sure you don't want to find the exact value. It's too difficult. Just I want the sign. -3 squared is 9. 9 minus 4 is 5. Cube it, it's positive. So negative times a positive divided by positive, negative. A -1. 2 times -1 is negative. I already know that's positive no matter what. -1. -1 squared, 1. 1 minus 4, -3. Cube it, it's negative. So I have 2 negatives in stuff involving only multiplication and division, positive. So that's positive. 1, 2 times 1, positive. That's automatically positive. 1 squared is 1. 1 minus 4 is -3. -3 cubed is a negative. So positive times positive divided by negative. 1 negative means negative. And finally, 3. 2 times 3, positive. That's already positive. Put a 3 here. 3 squared is 9. 9 minus 4 is 5. Cube it, positive. Okay. It would really be a bear to find the exact value. We don't care. We just need the sign. So positive. Right, we are doing the second derivative. Second derivative negative. concave down, concave down. Second derivative positive, concave up, concave up. So here are the intervals of concavity. F is concave down from negative infinity to -2, union 0 to 2. F is concave up from -2 to 0, union 2 to infinity. I do have an inflection point at 0, 0. Again, you do not have an inflection point at -2 or 2 because you don't have a point. Okay? Inflection point implies a point, an ordered pair, x comma y. There is no x comma y at either -2 nor 2. It's outside my domain. All right, so I'm ready for the whole graph. So here we go. Asymptote, asymptote. X-axis is an asymptote. Show you again. Horizontal asymptote, y is 0. Same as the x-axis. Vertical asymptote, x is plus or minus 2. Approach 0, approach 0. The only intercept, always decreasing, right? Decreasing, decreasing. Anywhere you pick a point on the graph, you're going down. The roller coaster is always going down, right? Concave down from -infinity to -2. So the roller coaster is going like this. Between -2 and 0, concave up. From 2 to infinity, back to concave down. And then from 2 to infinity, back to concave up. So there we go. Okay, and let me do my focus job for that again so you can see this. All right. Okay, so that was 13. See if I can do a couple more for you. 29. Y equals x minus 3, x to the 1/3. Okay. Now, I'm going to rewrite it in several ways to show you what's happening here. But this can be written as x minus 3 cube root of x. I can take the cube root of any real number, so the domain is all real numbers. But in terms of intercepts, it's best for me to do some factoring here. Okay, I factor out x to the 1/3. I know that's kind of a weird thing to factor out, but what led me to factor out the x to the 1/3 is I see x to the 1/3 right over here. So if I take an x to the 1/3 out of x, I have x to the 2/3 left, and then minus 3. Okay, so I claim that this is the same as that. If you're not sure about that, distribute it back out, right? What is that times that? X to the 1/3 plus 2/3 is 1. There it is. And then minus 3 x to the 1/3. But for solving for the intercepts, it's better to write it like that. Okay, so x to the 1/3 means cube root of x. X to the 2/3 means that. Okay, so domain is all real numbers. Okay, intercepts. I have the origin. I know that, plug in 0 and 0, but I have to work on this also. Okay, so 0 equals x minus 3 cube root of x. Move over to 3 cube root of x. Okay, so 3 cube root of x equals x. Then I cube both sides, raise both sides to the 3rd power to clean this up. Okay, so I have 3 cubed, which is 27. Cube root cube is just x, that's x cubed. Okay, subtract 27x, factor. 0 equals x times x squared minus 27. So that means x equals 0, we ought to get that. Or x squared minus 27 equals 0 means x squared equals 27. So by the square root property, x is plus or minus radical 27 or plus or minus 3 radical 3. Okay, so my intercepts are 0, 0, and plus or minus 3 radical 3 comma, 0. Okay, this is about 5.1 if you want to check that on your own. That's roughly 5.1. It's supposed to be a 5.1 there. All right, now symmetry. F of negative x. So we put negative x there and negative x there. Looks like that. This is a double negative situation. That's allowed here. Okay. So the cube root of negative x will be a negative. I distributed here. So it's negative x plus 3 cube root of x. This is the opposite of the original. It's negative parentheses x minus 3 cube root of x. And so the original was that. If I plug in negative x, I get the opposite of what I started off with, negative f of x. So I do have an odd function for origin symmetry. All right, let's see, are there any asymptotes? So I check n behavior. N behavior means what happens when x goes infinity or negative infinity. That's probably easier to see the factored form here. Okay, so right here, when x gets big, y gets big. That's pretty easy to see, right? Plug in a super big number here, that's positive, big. Super big number, subtract 3, it's super big. However, when x approaches negative infinity, y approaches negative infinity. So therefore, there's no asymptotes. One way you can verify that also is because you have an odd function. If it's odd, that means when x goes infinity, y goes infinity, the graph goes way out like that. Then by symmetry on this side, it has to go like that. When x approaches negative infinity, y approaches negative infinity. But if you want to work it out, okay, look over here. If I plug in a super big negative, this is a big negative. This is a big positive. Because I'm squaring it, that'll make it positive. Cube root is positive, take away 3. Remember, it's a big number, it's positive. So I have a big positive times a big negative. Big negative. Okay, so if I can just pause quickly and show you parts of the graph. This side goes way out here. When x goes to negative infinity, y goes to negative infinity. When x goes to positive infinity, y goes to positive infinity. And my intercepts are 0, 0, and plus or minus 3 radical 3, 0. There, there, and there. Okay. Right, so now for my derivative analysis. So let me use this. That's easiest for taking the derivative. So y prime is 1 minus x to the negative 2/3. 1/3 times 3 is 1, right? Then x to the negative 2/3, which I can rewrite as 1 minus 1 over x to the 2/3. Okay, double prime is a little bit clumsy. You can see what I have there, but the derivative of 1 is 0. So I have negative 1 times negative 2/3, that's positive 2/3, x to the negative 5/3, or 2/3 times 1 over x to the 5/3. Okay, so now I find critical numbers. X equals 0 is a critical number. It's not allowed. It is in the domain. The domain was all real numbers. So x equals 0 is a critical number. It's a no-no. Now set y prime equal to 0. So 1 minus 1 over x to the 2/3 is 0. Move that over. 1 equals 1 over x to the 2/3. Cross multiply. X to the 2/3 equals 1. Raised to the 3/2, but you need a plus or minus. Okay, so x is plus or minus 1. Okay. 1 works, negative 1 also works. Okay, look back over here. I plug in 1, right? 1 to the 2/3 is 1. 1 minus 1 is 0. Negative 1 also works because by rule, negative 1 squared is 1. Cube root of 1 is 1. And 1 over 1 is 1, and then 1 minus 1 is 0. So my critical numbers are 0 and plus or minus 1. All right, I already got the origin. Okay, when you plug in 1, you get negative 2, and when you plug in negative 1, you get 2. Let's double check that. Plug in 1 here. and a 1 here, I have 1 minus 3, which is -2. And when you plug in -1, maybe I'll just appeal to symmetry. Since I have symmetry with respect to the origin, if I have 1, -2, that gives me -1, 2. Okay, so now for my sine chart, y prime was 1 minus 1 over x to the 2/3. Okay, -1, 0, 1. So pick something over here. I actually picked -8 because it comes out nice. And I picked -1/8. Believe it or not, that comes out nice. +1/8. And then 8. Okay, now why does that come out nice? Let me start with an easy one, 8. 8 to the 2/3 means cube root first, right? That's the reason why I picked 8. So what's the cube root of 8? 2. 2 squared is 4. So I have 1 minus 1/4. That's positive. Okay. If I plug in 1/8, you start off with a cube root. Cube root of 1/8 is 1/2. Square it, you have 1/4. 1 divided by 1/4 is 4. 1 minus 4, negative. Okay, then I'll do the harder ones, but now that you see the pattern, hopefully you can get that. -8, cube root of -8. That's what the 3 means. -2. -2 squared is 4. So I have 1 minus 1/4, positive. -1/8. Plug in -1/8. Cube root, -1/2. Square it, 4. 1/4, sorry. 1 divided by 1/4 is 4. 1 minus 4, negative. Okay, positive, negative, negative, positive. Increasing, decreasing, decreasing, increasing. So intervals of increase and decrease, f is increasing from -∞ to -1, union 1 to infinity. F is decreasing, -1 to 0, union 0, 1. Okay. The graph goes up and then down. That means -1, 2 is a maximum. Down, down, neither maximum nor minimum. Down, up, minimum. So 1 comma -2 is a minimum. All right, then the second derivative came out to be this thing. I had 2/3, 1 over x to the 5/3. That can never equal 0. The numerator is already 2. And yeah, I have 2/3 times 1, which is now 2. So 2/3 x to the 5/3. Okay. Well, if I plug in a negative, it'll be negative. If I plug in a positive, it'll be positive. Right, if I plug in -1, -1, cube root is -1, raised to the 5th power is -1, top is positive, negative. Plug in +1, positive. So concave down, concave up. So the function is concave down from -∞ to 0, concave up from 0 to infinity. Hence, I do have an inflection point at the origin. So here we go. Intercept, -3 radical 3, 0, 0, 0, 3 radical 3, 0. -1, 2 is a max. 1, -2 is a min. Graph goes increasing, decreasing, decreasing, increasing. Increasing, decreasing, decreasing, increasing. Okay. Up until 0, concave down, upside down U shape. The rest of the time, U shape. And here's the other thing. Okay, I have to draw it so that we have a vertical tangent. This is a vertical tangent. So there is a tangent line, but it's vertical, which means the slope is undefined. Okay. So I can't make it my regular inflection point where I just kind of go like so. In other words, you shouldn't draw it like this. So you don't want that. That has a slope, looks like it's negative. Here you have an undefined slope. It's still smooth. So this would be an acceptable ride on a roller coaster, I suppose. Maybe you've been on roller coasters, go like this, goes like that, and then it comes down. It looks like you're looking straight down, right? And then it switches back down over like that. Okay. So that's 29. Let me show you everything with that. And how much time do I have? Let me see if I can get you started on the last problem. If I don't finish it, that's okay. I can still do tomorrow. But otherwise, I was going to be done with the section. I'll get started with 4.7 tomorrow. And that's that. Okay. All right. The last one I was going to show you was 45. And we'll see how much time I have to do. All right. So y equals 1 over x plus natural log of x, which I can think of as x at a negative 1 plus natural log of x. All right, intercepts. X equals 0, can't do it, right? Y equals 0, you can't easily solve that, but it's going to show up a little bit later. So we'll have to hold off on that. Okay, normally, there's no easy way to solve an equation that has a log mixed up with a rational expression. So we can't solve it. Fortunately, if you guess a number, you might be able to see something that works. Okay, can you guess a nice number? 1, right? 1 would work. Natural log of 1 is 0. Oh no, I take it back. That's actually not true. Forget what I said. Okay, yeah, I messed up on my graph here also, but we'll see. We can't solve that, but we'll come back to it. There isn't going to be any. Okay, symmetry, there's none. Okay, once you have this, right, the domain is 0 to infinity, you automatically can't have any symmetry. So the whole graph, which I'll show you here, you can't have any symmetry with respect to the y-axis because that means there's a graph over here. And you can't have symmetry with respect to the origin, otherwise there'll be a graph over here. So it automatically means that's not true. There's no symmetry. By the way, I just forgot to mention the previous graph. You do have origin symmetry. So let's say that point reflects over there, that reflects there. A point here would reflect across the origin over there, and so on. All right, asymptotes. Well, when x approaches infinity, I say y approaches infinity. 1 over big is 0, but ln x approaches infinity. So 0 plus a big number is a big number, approaches infinity. Now, what's a little bit tougher is what happens when limit x approaches 0 from the right of 1 over x plus ln x. Okay, because this approaches negative infinity, this approaches positive infinity. So what should I do? Okay, so what I did was I got a common denominator, 1 over x plus x ln x over x. Okay. In order to do this, I have to say what happens as the limit as x approaches 0 from the right of x ln x. Okay, I'm only going to work on this. That's the only thing that bothers me right now. X ln x. So I'm taking a little time out, figuring this out. All right, I want to use L'Hopital's rule. To use L'Hopital's rule, I need a quotient. So I play this trick. Multiplying by x is the same as dividing by 1 over x, which I'm going to write as x at negative 1 for derivative purposes. Okay, and now I have infinity over infinity. Okay, when x approaches 0 from the right, natural log function drops to negative infinity. It's okay, you can still write infinity. It's allowed. And when I plug in 0.001, that also approaches infinity. So it is infinity over infinity. So L'Hopital's rule applies. Derivative of the top is 1 over x. Derivative of the bottom, which again I'm going to treat as x at negative 1, is negative x at a negative 2. Okay, x at a negative 2 on the bottom means x squared on top. Slide the x on the bottom, there's a negative. So I have the limit as x approaches 0 from the right of negative x, and that is 0. So bottom line, this thing approaches 0, x ln x. I needed that when I finally get back to this. Okay, so at this stage, I had limit as x approaches 0 from the right of 1 plus ln x over x. Okay, I now know that this thing approaches 0. So if I cover this up, right, this approaches 0. I have 1 over x. Okay, that's 0. We just did that over here. So 1 over 0.0001, that approaches infinity. So the y-axis is an asymptote, shoots up like that. Okay. I guess I should say a vertical asymptote is x equals 0, which is the same thing as the y-axis. Okay, so I'll do my derivative analysis now. So y prime, start off with this. So the first derivative is negative x at a negative 2 plus 1 over x. Okay, for second derivative purposes, I'm going to write it like this. Negative x at a negative 2 plus x at a negative 1. But better for algebra is to write it like this. Negative 1 over x squared plus 1 over x. Double prime, differentiate this. So that's going to be positive 2 x at a negative 3 minus x at a negative 2. And then better for algebra, 2 over x cubed minus 1 over x squared. Okay, so set y prime equal to 0. There was my y prime. Negative 1 over x squared plus 1 over x equals 0. Multiply both sides by x squared to make it nicer. So after doing that, I get negative 1 plus x equals 0, or x equals 1. Okay, plug in 1 to the original. 1 over 1 plus natural log of 1. Natural log of 1 is 0. So I have 1 comma 1. Sine chart. Y prime is negative 1 over x squared plus 1 over x. I have to put down 0 because I'm not allowed to go past 0, right? So I have to plug in a number like 0.5. Okay, if you plug in 0.5, you'll show that it's decreasing. Okay, 0.5 squared is 0.25. Negative 1 divided by that is negative 4. Negative 4 plus 2, it's negative. If I plug in 2, that's like negative 1/4 plus a half, that's positive. Okay, so the function is decreasing from 0 to 1, increasing from 1 to infinity. That means 1, 1 is a minimum. That's all the graph does. So this is actually even an absolute minimum. How is it absolute? All it does is goes down and goes up. So it's an absolute minimum. So that now goes back to this for intercepts. There aren't any. Okay. So now I can dogmatically say there's no intercepts. All right, then y double prime equal to 0. So double prime came out to be this thing. 2 over x cubed minus 1 over x squared equals 0. Clean it up by multiplying both sides by x cubed. X cubed times that is 2. X cubed times that is negative x equals 0. So x equals 2. Plug back in 2. I have 1/2 plus natural log of 2. That's approximately 1.193. I need to know where that was in order to graph it. All right, so sine chart for y double prime, 0, 2. Okay, plug in 1. 2 minus 1, positive. Okay. I plugged in 3 because I thought the calculation was a little bit nicer here. If I put a 3 here, that's 2 over 27 minus 1 over 9. That's 2 over 27 minus 3 over 27. That's a negative. So it's concave down. Concave up, concave down. So f is concave up only from 0 to 2. You can't say from negative infinity to 2 because the graph, there is no graph out there. The domain is only 0 to infinity. So concave up from 0 to 2. concave down from 2 to infinity. So this 0.2 comma 1/2 ln2 is an inflection point. And here is the graph. Okay, I had to come down to the x-axis. It doesn't come to the x-axis. That's 1, 1. That's a minimum. Okay, so decreasing, increasing, minimum, concave up, inflection point switches over to concave down, but still increasing after that. And there we go. Okay, so I'm done, folks. Let me just do my focus thing, and then that's that. So that's as much of the curve sketches as I was going to do. I think I've already done 6 of them. Yes, they're long. Okay, but I think I've shown you enough to see what's going on. Okay, so we don't have to do 4.6 again. So I'll start some of 4.7 tomorrow, looks like. So there's that. Okay, so I'm done, folks. If you missed the roll call, put your name in the chat right now. Anybody have any quick last-minute questions? Otherwise, that's it for today. If you join late, put your name in the chat. All right, so that'll be it for today, folks. So have a good day, and we'll see everybody next time. Okay, bye, everybody.